Have you ever paused in the middle of an ordinary moment and felt the stillness around you? The air perfectly calm, your coffee undisturbed, the ground solid beneath your feet. Everything feels motionless, frozen, at rest. But what if I told you that right now, at this very second, you're hurtling through space at speeds that would make a bullet seem like it's standing still? The Earth beneath you spins at over 1,000 miles per hour. At the same time, our entire planet races around the Sun at 67,000 miles per hour. And while all of that happens, the solar system itself barrels through the Milky Way galaxy at nearly 490,000 miles per hour. Beyond even that, our galaxy tumbles through space at over 1.3 million miles per hour, carried by forces we're only beginning to understand. Yet somehow, impossibly, you feel none of it. Not a tremor, not a whisper of motion. The illusion of stillness is so perfect that ancient humans believed Earth was the center of an unmoving universe. But the truth is far more beautiful and far more strange. Everything spins, from the smallest particle to the largest galaxy, from the electron orbiting an atom to the supermassive black hole at the heart of the cosmos. Rotation is the universe's most fundamental rhythm. Tonight, we're going to drift into that mystery together. We'll ask not just why things move, but why they can never stop moving. Why rotation seems to be written into the very fabric of reality itself. So close your eyes if you'd like, let the sound of these words wash over you, and follow me into the spinning heart of everything. Before we begin our journey, if you're kind enough, a gentle like or a quiet tap on subscribe would mean the world to me. It's a small gesture, but I hold it with deep gratitude because every bit of your support keeps this tiny universe alive and reminds me that these quiet stories still find their way to gentle hearts like yours. Now, let's begin. Part 1. The Great Illusion of Stillness. When Galileo first turned his telescope toward Jupiter in 1610, he saw something that would change humanity's understanding of motion forever. 4 tiny points of light circle the giant planet, appearing and disappearing as they orbited. These moons of Jupiter weren't fixed in place. They were moving, dancing in an endless rotation around their parent world. For the first time, humans could see with their own eyes that motion was natural, constant, and universal. The heavens weren't frozen, they were alive with spin. But here's what makes this so profound. Those Jovian moons travel at thousands of miles per hour, yet from our perspective, they seem to glide serenely, almost motionless. Just like us on Earth, the inhabitants of those worlds, if any existed, would feel nothing of their motion. The coffee in their cups wouldn't ripple, the air wouldn't drag. They would stand on their spinning worlds and feel perfectly, utterly still. This is the great cosmic illusion. Motion feels like stillness when everything moves together. The reason we don't feel Earth's rotation comes down to a principle so simple, yet so profound, that it underlies all of physics: inertia. Isaac Newton described it in his first law of motion in 1687. An object in motion stays in motion unless acted upon by an external force. You, the air around you, the oceans, the mountains, every atom of this planet is moving together as one unified system. There's no relative motion between you and your surroundings, so there's nothing to feel. Think of it this way. When you're sitting in a car travelling down a smooth highway at 60 miles per hour, you can sip your coffee, read a book, even balance a coin on your finger. The motion is constant and uniform, so you perceive stillness. Only when the car accelerates, brakes, or turns do you feel movement. That's because your body experiences a change in velocity, a force acting upon you. Earth's rotation is the ultimate smooth ride. It's been spinning for 4.5 billion years at nearly the same speed, with no sudden stops, no sharp turns. According to NASA's Goddard Space Flight Center, the planet completes one full rotation every 23 hours, 56 minutes, and 4 seconds. That's what astronomers call a sidereal day, the true measure of Earth's spin relative to distant stars. At the equator, where Earth's circumference is greatest about 24,901 miles, the surface moves at roughly 1,037 miles per hour. As you move toward the poles, that speed decreases because the circumference of the spinning sphere gets smaller. At 45 degrees latitude, roughly the latitude of Portland or Milan, the rotational speed drops to about 733 miles per hour. And at the poles themselves, you'd be spinning in place, completing one rotation every 24 hours, but barely moving through space at all. Yet none of this motion registers in your body. Your inner ear, which evolved to detect balance and acceleration, simply can't sense uniform velocity. It responds to changes in motion, not motion itself. That's why you feel a lurch when an elevator starts moving, but not the smooth ride once it reaches constant speed. Astronauts aboard the International Space Station experience this illusion on an even grander scale. The ISS orbits Earth at approximately 17,500 miles per hour, circling the planet every 90 minutes. Inside the station, astronauts float effortlessly, their bodies in a state called microgravity. But they're not escaping Earth's gravity. They're constantly falling toward Earth, and the station is too. The trick is that they're moving forward so fast that as they fall, Earth's surface curves away beneath them at the same rate. They're perpetually falling and perpetually missing the ground. And yet, inside that spacecraft hurtling through space at 5 miles per second, everything feels calm. Without air resistance, without friction, motion feels like stillness. Astronauts can drink floating spheres of water, play with spinning objects, and sleep soundly while travelling, faster than any human on Earth's surface. This phenomenon has a name: uniform motion. It's the same principle that allows you to sip tea on an airplane cruising at 500 miles per hour, or sleep peacefully on a train racing through the night. As long as the motion is smooth and constant, your senses perceive rest. But here's where it gets even more beautiful. Earth's motion doesn't stop with its rotation. While spinning on its axis, our entire planet orbits the Sun at roughly 67,000 miles per hour. That means every second, we travel about 18.5 miles through space. In the time it took you to read this sentence, you've travelled nearly 200 miles along Earth's orbital path, and even that's not the end. Our solar system itself, Sun and planets together, orbits the centre of the Milky Way galaxy. We're located about 26,000 light years from the galactic core, and we complete one full orbit every 230 million years. The last time Earth was in this exact position in the galaxy, dinosaurs had just begun to emerge. The speed of this galactic orbit? Approximately 490,000 miles per hour. And beyond even that, our entire galaxy is moving through space, pulled by the gravity of nearby galaxy clusters and pushed by the expansion of the universe itself. Recent measurements suggest the Milky Way is travelling at over 1.3 million miles per hour, relative to the cosmic microwave background, the faint afterglow of the Big Bang. Let me pause and let that sink in. Right now, as you sit or lie in perfect stillness, you're travelling through the cosmos at over 1 million miles per hour. The numbers are so large they lose meaning. But the motion is real, constant, and utterly imperceptible. Neil deGrasse Tyson once said, "We're on a space rock that is orbiting a star that is orbiting a galaxy that is moving through the universe, and we call it home." It's a humbling thought. Our sense of stillness is an artifact of scale and symmetry. The universe moves together, and we move with it. Still, scientists have found ways to measure this hidden motion with remarkable precision. One of the most elegant demonstrations is the Foucault pendulum, first revealed to the world in 1851 by French physicist Léon Foucault. He suspended a 62-pound brass sphere from the dome of the Pantheon in Paris using a 220-foot wire. As the pendulum swung back and forth, something extraordinary happened. The pendulum's plane of oscillation slowly rotated clockwise, completing a full circle in about 32 hours. Foucault hadn't moved the pendulum, the floor beneath it had moved. Earth's rotation caused the ground to turn while the pendulum, following the laws of inertia, maintained its original direction in space. The rate of rotation depends on latitude. At the poles, a Foucault pendulum completes a full circle in exactly 24 hours. At the equator, it wouldn't rotate at all because Earth's spin and doesn't twist the pendulum's motion there. Anywhere in between, the rate varies with the scene of the latitude. It's a beautiful mathematical relationship, a direct visual proof of Earth's rotation that requires no telescopes, no satellites, just a swinging weight and patience. If you've ever stood near one of these pendulums in a museum, watching it knock over pegs arranged in a circle, you've witnessed something profound. You've seen time and motion merge, the invisible spin of the planet revealed through the slow, hypnotic swing of a brass sphere. On a cosmic scale, this rotation is far from trivial. Earth's spin does more than define day and night. It stabilizes our climate, generates our magnetic field, and creates the Coriolis effect, the invisible force that shapes weather patterns and ocean currents. Without Earth's rotation, one side of the planet would face the sun perpetually, baking under endless daylight while the other side froze in eternal darkness. The boundary between them would be a violent twilight zone, a ring of perpetual storms where hot and cold air clashed without mercy. Life as we know it could not exist in such a world, but because Earth spins, energy from the sun is distributed more evenly. Sunlight sweeps across the surface in a steady rhythm, allowing temperatures to moderate, oceans to circulate, and ecosystems to thrive. The 24-hour cycle of day and night has become the heartbeat of life, a rhythm so deeply embedded in biology that every living organism carries an internal clock synchronized to it. According to research from the National Center for Biotechnology Information, circadian rhythms, the molecular timekeepers inside every cell, evolved to match Earth's rotation. These rhythms regulate when plants open their leaves to sunlight, when animals hunt or sleep, and when human bodies release hormones like melatonin and cortisol. Disrupt this rhythm, as shift workers and travellers across time zones know all too well, and health suffers. Our bodies are literally tuned to the planet's spin. Earth's rotation also powers something even more vital, the magnetic field. Deep beneath our feet, about 800 miles below the surface, lies Earth's outer core, a churning sea of liquid iron and nickel heated temperatures exceeding 4,000 degrees Celsius. As the planet spins, this molten metal flows in complex patterns, generating electric currents. These currents, in turn, create a magnetic field that extends far out into space, forming an invisible shield called the magnetosphere. NASA's magnetospheric multiscale mission has studied this protective bubble in exquisite detail. The magnetosphere deflects the solar wind, a constant stream of charged particles emitted by the sun. Without this shield, those particles would strip away Earth's atmosphere molecule by molecule, just as they did on Mars billions of years ago. Mars once had a magnetic field generated by its own spinning core, but the red planet is smaller than Earth, and its interior cooled faster. As the core solidified, the magnetic dynamo shut down. Without protection, Mars lost most of its atmosphere to space, leaving behind the cold, dry desert we see today. The difference between Earth and Mars, between a living world and a dead one, comes down in large part to rotation and the magnetic field it sustains. Here on Earth, that magnetic field creates one of nature's most beautiful phenomena, the aurora. When charged particles from the sun collide with atoms in our upper atmosphere, they transfer energy, causing those atoms to glow. Near the poles, where Earth's magnetic field lines converge, these collisions are most intense, painting the night sky with shimmering curtains of green, red, and purple light. I've seen the aurora once, from a cold hillside in Iceland. The lights moved like living things, rippling and folding, soundless but somehow singing. It felt like watching the planet breathe. And in a way, that's exactly what it was. The visible interaction between Earth's magnetic breath and the solar wind. A reminder that our spinning world is protected, shielded, alive. But there's something even stranger about Earth's rotation. It's not constant, not quite. The length of a day, that seemingly fixed 24 hours, has been changing throughout Earth's history. When the planet first formed 4.5 billion years ago, a day lasted only about 6 hours. The young Earth spun much faster, completing a full rotation in a quarter of the time it takes today. What slowed it down? The Moon. Billions of years ago, a Mars-sized object called Theia collided with the young Earth in a cataclysmic impact. The debris from that collision coalesced into the Moon, our celestial companion. Ever since, the Moon's gravity has been pulling on Earth's oceans, creating tides. These tidal bulges act like a brake on Earth's rotation, gradually slowing the planet's spin. As Earth loses rotational energy, the Moon gains it, slowly drifting away from us. Using laser reflectors placed on the lunar surface by Apollo astronauts, scientists can measure this drift with millimeter precision. The Moon recedes from Earth at about 1.5 inches per year. It's a tiny change, imperceptible in a human lifetime, but over geological timescales, it adds up. NASA's Jet Propulsion Laboratory has calculated that Earth's rotation is slowing by about 1.7 milliseconds per century. That means our days are getting longer, though we'll never live long enough to notice. This gradual slowing has profound implications. About 620 million years ago, a day on Earth lasted only 21.9 hours. Coral fossils from that era showed daily growth rings, recording the rhythm of ancient tides and confirming the shorter day length. Going back even further, to the time of the earliest life 3.5 billion years ago, a day may have been only 12 to 15 hours long. Life evolved under a different sky, a faster rhythm, a younger planet spinning in the light of a younger sun, and the slowing continues. Billions of years from now, if Earth and the Moon both survive the sun's eventual expansion into a red giant, our planet's rotation will lock completely with the Moon's orbit. Each will always show the same face to the other, just as the Moon already does to us. A day will last about 47 current days, and the Moon will hang motionless in the sky, visible from only one hemisphere. The tides will cease, and the dynamic interplay between Earth and Moon will settle into a final, eternal stillness. But for now, we spin. We turn beneath the stars, ancient and relentless, unaware of the vast speeds at which we move. The illusion of stillness is perfect because everything moves together, a cosmic ballet so smooth and synchronized that only the most careful measurements reveal the truth. Take a slow breath. You're spinning right now. You always have been. And the silence you hear, the calm you feel, is simply the sound of everything moving in perfect harmony. Now let's drift deeper. Let's ask the question that haunts every astronomer, every physicist, every curious mind that looks up at the night sky. If everything spins, Who set it spinning? Where did the first rotation begin? That's where our next chapter takes us, back to the very first second of time itself. Part 2, The Origin of Spin, tracing rotation to the beginning. If you could rewind the universe like a cosmic film, playing backward through 13.8 billion years of history, what would you see? Galaxies spiraling inward, stars collapsing, planets dissolving, atoms unraveling. Keep going, further back, beyond the first stars, beyond the first atoms, beyond even light itself. You'd arrive at a moment so dense, so hot, so incomprehensibly energetic that our laws of physics begin to blur. This is the Planck epoch, the first 10 or 43 seconds after the Big Bang. Time and space themselves were newborn. Quantum foam bubbling at scales smaller than anything we can measure. And somewhere in that primordial chaos, the first spin began. The question of where rotation comes from is not philosophical. It's deeply physical, rooted in the mathematics of cosmology and the quantum fluctuations that gave birth to structure. Today, scientists studying the cosmic microwave background, the faint afterglow of the Big Bang, have found tantalizing clues that the universe may have been born spinning. The cosmic microwave background, or CMB, is the oldest light in the universe. It was released about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into hydrogen atoms. Before that moment, the universe was an opaque plasma, light scattered endlessly by free electrons. But once atoms formed, light could travel freely, and it's been travelling ever since, stretched and cooled by the expansion of space into microwaves. NASA's Wilkinson Microwave Anisotropy Probe, BUMAP, and later the European Space Agency's Planck satellite mapped this background radiation with extraordinary precision. They found tiny temperature variations, hot spots and cold spots, differing by only a few millionths of a degree. These ripples represent density fluctuations in the early universe, the seeds from which galaxies would eventually grow. But there was something else in the data, something stranger. Some researchers noticed a faint alignment in the distribution of these ripples, a large-scale pattern that seemed to suggest a preferred direction in space. They called it the axis of evil, a tongue-in-cheek name for a mystery that shouldn't exist. If the universe were truly isotropic, the same in all directions, as most cosmological models predict, there should be no such alignment. One possible explanation: the universe itself may have a subtle, large-scale rotation. In 2011, physicist Michael Longo from the University of Michigan analysed the rotation directions of over 15,000 spiral galaxies from the Sloan Digital Sky Survey. He found a small but statistically significant asymmetry. Galaxies in one half of the sky tended to rotate in one direction more often than the other. It was a weak signal, but persistent. If true, this could mean the universe carries a memory of rotation from its very beginning. A primordial twist that, billions of years later, still influences how galaxies spin. But how could such a rotation begin? The answer likely lies in quantum mechanics and something called quantum fluctuations. Even in a perfect vacuum at the smallest scales, space is never truly empty. Virtual particles pop in and out of existence, energy fields jitter and sway, obeying the strange rules of Heisenberg's uncertainty principle. When the Big Bang occurred, the universe underwent a brief but staggeringly fast expansion called cosmic inflation. In a fraction of a second, space expanded exponentially, doubling in size again and again faster than the speed of light. This inflationary period, proposed by physicist Alan Guth in 1981, explains why the universe looks so smooth and uniform on large scales. But here's the crucial part. Inflation didn't just smooth out the universe. it also amplified quantum fluctuations. Tiny random variations in energy, smaller than an atom, were stretched to cosmic scales. Those fluctuations became the seeds of structure, the slight differences in density that would later collapse into stars and galaxies. And some of those fluctuations carried angular momentum, quantum spin. According to research from NASA's Goddard Space Flight Center, during inflation, subtle rotational modes called B-modes may have existed in the primordial gravitational waves. These are tiny curls in space-time, twists imprinted by the universe's first spin. If detected, they would be the fossil record of rotation, proof that the cosmos was born turning. Experiments like BICEP-2 and the forthcoming Lightbird satellite are searching for these B-modes in the polarization of the CMB. Finding them would be monumental. It would confirm that rotation is not something that happened to the universe. It's something the universe has always had. Even the laws of physics hint at this. In quantum mechanics, every particle carries an intrinsic property called spin. Electrons, protons, neutrons, even photons all have spin. It's not literal spinning like a top, but a fundamental angular momentum, a property as basic as mass or charge. Richard Feynman once said, "Spin is one of the most profound mysteries of nature. The electron doesn't spin the way a planet spins. It simply has spin built into its existence." So in a way, rotation wasn't added to the universe later. It was baked in from the start. Every particle, every force, every interaction carries the signature of angular momentum. When the universe was less than a second old, it was filled with a soup of quarks, gluons, and other fundamental particles, all jostling in a state of unimaginable heat and density. As the universe expanded and cooled, these particles began to combine, forming protons, neutrons, and eventually atoms. Each carried tiny amounts of angular momentum. When gravity later gathered them into clouds, that momentum was conserved. This is the principle of conservation of angular momentum, one of the most sacred laws in physics. If something is spinning and no external force stops it, it keeps spinning. In fact, if it shrinks, it spins faster. Think of a figure skater pulling in her arms during a spin. Her rotational speed increases dramatically because her angular momentum must remain constant. As her body becomes more compact, she spins faster to compensate. The same principle governs the formation of stars and galaxies. When a massive cloud of gas and dust begins to collapse under its own gravity, it shrinks, and as it shrinks, it spins faster. The angular momentum that was barely noticeable in the diffuse cloud becomes dramatic as the matter concentrates. This is why newly forming stars are surrounded by spinning disks of material, the birthplaces of planets. Our own solar system formed this way 4.6 billion years ago. A cloud of gas and dust, perhaps disturbed by a nearby supernova, began to collapse. As it collapsed, it spun faster, flattening into a rotating disk. At the center, the sun ignited. Around it, planets coalesced from the remaining material, each inheriting a portion of the original angular momentum. That's why all the planets orbit the sun in the same direction. It's why most of them rotate in the same direction too. They're all carrying the memory of that primordial spin, a rotation that began in the interstellar cloud and continues today. Even the sun spins, completing one rotation every 27 days at its equator, though its poles rotate more slowly. This differential rotation generates powerful magnetic fields that shape solar flares and coronal mass ejections. When those magnetic storms reach Earth, they create auroras and can even disrupt satellites and power grids. Everywhere we look, rotation is not an accident. It's a consequence of how the universe began. In 2020, astrophysicist Lior Shamir from Kansas State University published a study analysing over 200,000 galaxies from multiple sky surveys. He found that galaxies in different regions of the universe show a subtle but consistent directional preference in their rotation. This suggests that the universe may have a large-scale rotational structure, a cosmic spin axis that has existed since the beginning. As Shamir wrote, the universe may have a preferred direction of rotation, a signature of angular momentum imprinted during the Big Bang. This doesn't mean the universe spins like a giant top. Rather, it suggests that space-time itself may have a slight twist, a subtle curvature that cascades across billions of light years. Testing this idea is extraordinarily difficult. The signals are faint, buried in noise and distorted by cosmic expansion, but the evidence is slowly accumulating. The James Webb Space Telescope, with its unprecedented ability to observe distant galaxies, is already finding surprises. JWST has detected galaxies that formed just 300 million years after the Big Bang, less than 3% of the universe's current age. Even at that early epoch, these galaxies show organised rotation. They have spiral structures, spinning disks, clear signs of angular momentum. That means the seeds of spin were planted almost immediately. The universe didn't learn to rotate, it was born rotating. Some cosmologists have proposed that dark matter, the invisible substance that makes up 85% of all matter, also carries rotational signatures. Computer simulations by NASA's Jet Propulsion Laboratory show that dark matter halos, the invisible scaffolding around galaxies, twist and rotate over billions of years. This rotation guides the visible matter within them, like leaves caught in a whirlpool. Without that rotation, galaxies would tear themselves apart. The stars would fly outward, no longer bound by gravity. But because both visible and dark matter rotate together, galaxies remain stable, spinning gracefully through the cosmic night. There's even speculation that the universe's first spin could be linked to the arrow of time, the fact that time flows in one direction from past to future. In physics, most fundamental laws are time-symmetric. They work equally well forward and backward. But entropy, the measure of disorder, always increases. That's the second law of thermodynamics, and it gives time its direction. Some physicists believe that the universe's initial low entropy state, its organised beginning, was related to its rotational structure. If true, then the spin of the cosmos and the flow of time are intertwined at the deepest level. As ESA cosmologist Jan Tauber once said, the universe carries memory not in words but in patterns of light, and within those patterns lies the faint signature of the first motion, a twist older than time itself. So when we ask who set the universe spinning, the most honest answer is, nobody had to. The universe was born in motion. Spin wasn't created. It was inherited from the quantum foam of the Planck epoch, amplified by inflation and preserved by the conservation of angular momentum. Every galaxy, every star, every atom carries that ancient rotation. It's the most fundamental rhythm in existence, a beat that has never stopped, not once, in 13.8 billion years. Take a breath. The atoms in your body are still turning with that first impulse. From the tiniest electron to the swirl of the Milky Way, the same rotation continues, unbroken, eternal. And as we drift forward through this story, we arrive at a question that flows naturally from the origin of spin. If rotation began the universe, could it also be the force that makes life possible? Could the spin of our world, our galaxy, our cosmos be the reason you're here right now? Breathing, thinking, alive? That's where we turn next. Part 3. How spin creates the conditions for life. Without rotation, Earth would be a silent tomb. No seasons, no weather, no flowing rivers, just two hemispheres, one scorched by eternal daylight, the other locked in frozen darkness. Between them, a narrow twilight band where howling storms rage without end. Nothing could live there, nothing could grow, but because Earth spins, because it completes one full rotation every 24 hours, our planet breathes. Energy from the sun is distributed across the surface in a steady, predictable rhythm. Temperatures moderate, oceans circulate, winds blow. Life, in all its staggering diversity, flourishes in the space that rotation creates. The spin of our world is not a minor detail. It's the engine that drives everything. Let's start with the most obvious effect: day and night. As Earth rotates, different parts of the surface face the sun. When your hemisphere tilts toward the sun, it's daytime. When it tilts away, night falls. This alternation creates temperature gradients, differences in heat that drive atmospheric circulation. Without rotation, one side would heat continuously, while the other cooled forever. The temperature difference would be catastrophic. The day side might reach hundreds of degrees, while the night side plunged to hundreds of degrees below zero. The boundary between them would be a chaotic transition zone, where superheated air clashed with frigid darkness, generating unstoppable storms. But with a 24-hour rotation, sunlight sweeps around the globe in a gentle wave. Daytime warms the surface, nighttime cools it, but not too much. The rotation spreads the energy evenly enough that stable climate zones can form. This rhythm has been Earth's heartbeat for 4.5 billion years, and life has adapted to it so completely that the 24-hour cycle is written into the DNA of every organism. Scientists call these internal clock circadian rhythms from the Latin words circa, about, and diem, day. Even single-celled bacteria have molecular timekeepers that sync to the day-night cycle. Plants open their leaves at dawn and close them at dusk. Animals hunt, forage, and sleep according to the rhythm of rotation. Humans release hormones like cortisol and melatonin on a 24-hour schedule, regulating wakefulness and sleep. According to research published by the National Center for Biotechnology Information, disrupting circadian rhythms leads to serious health problems: sleep disorders, depression, metabolic dysfunction, even increased cancer risk. Our bodies are not just influenced by Earth's rotation, they're synchronized to it at the cellular level. If Earth stopped spinning, this biological harmony would shatter. The regular pulse of light and dark would vanish, replaced by endless day or endless night, depending on where you stood. Life, evolved over billions of years to match the planet's rhythm, would struggle to adapt. Most species would perish. But rotation does more than create day and night. It powers Earth's magnetic field, one of the most critical shields for life. Deep beneath our feet, about 1/800 miles below the surface, lies Earth's outer core. This is a sea of molten iron and nickel, heated to over 4,000 degrees Celsius by the decay of radioactive elements and residual heat from the planet's formation. As Earth spins, this liquid metal flows in complex swirling patterns. Those flows generate electric currents, and those currents, in turn, create a magnetic field. It's a natural dynamo powered by rotation. NASA's magnetospheric missions have mapped this field in exquisite detail, showing that it extends tens of thousands of miles into space, forming an invisible bubble called the magnetosphere. This magnetic shield is what stands between life and the sun's fury. Our star constantly emits a stream of charged particles, the solar wind, moving at over 1 million miles per hour. Without Earth's magnetic field, these particles would strike the atmosphere directly, stripping away molecules one by one. We know this can happen because we've seen it happen elsewhere. Mars. Mars is roughly half the size of Earth, and it cooled faster. As its interior solidified, the magnetic dynamo shut down. The red planet once had a thicker atmosphere, liquid water on its surface, perhaps even conditions suitable for life. But without a magnetic field, the solar wind eroded that atmosphere over billions of years. Today, Mars is cold, dry, and dead, its air 100 times thinner than Earth's. The difference between Earth and Mars, between a living world and a barren one, comes down largely to rotation. Earth's spin keeps the core molten and churning, generating the magnetic field that preserves our air, our water, our climate, and there's a visible reminder of this protection: the aurora. Near Earth's magnetic poles, where field lines converge, charged particles from the solar wind spiral downward into the atmosphere. When they collide with oxygen and nitrogen molecules, they transfer energy, causing those molecules to glow. The result is the aurora borealis and aurora australis, shimmering curtains of green, red and purple light dancing across the polar skies. I'll never forget the first time I saw the aurora. I was in northern Norway, standing on a frozen lakeshore under a sky so clear I could see the Milky Way arcing overhead. Then, slowly, the horizon began to glow. Green light rippled like water, folding and twisting, soundless but alive. It felt like watching the planet breathe, like seeing the invisible magnetic field made visible for just a moment. The aurora's beautiful, yes, but it's also a reminder that we live on a spinning, protected world, shielded by forces we cannot see but depend on absolutely. Rotation also shapes the way air and water move across the planet. This is the Coriolis effect, one of the most elegant consequences of Earth's spin. Imagine you're standing at the North Pole and you throw a ball toward the equator. From your perspective, the ball travels in a straight line. But here's the trick: the ground beneath it is also moving. The equator spins faster than the poles because it has a larger circumference, so as the ball travels south, it appears to curve to the right. This apparent curve isn't caused by any force pushing on the ball. It's caused by the difference in rotational speed between your starting point and your destination. And it happens everywhere on Earth, to everything that moves across significant distances. The Coriolis effect is why hurricanes spin. In the northern hemisphere, low-pressure systems rotate counterclockwise. In the southern hemisphere, they rotate clockwise. The rotation is driven by Earth's spin beneath the storm. It's why ocean currents form vast gyres, circular patterns that distribute heat around the planet. The Gulf Stream, for example, carries warm water from the tropics to the North Atlantic, moderating Europe's climate. Without Earth's rotation, that current wouldn't exist. It's even why large-scale wind patterns, like the jet streams, flow west to east. The Coriolis effect bends the air as it moves, creating the prevailing winds that have shaped human history. Ancient sailors navigated by these winds, and modern aviation still depends on them. NASA's Global Modelling and Simulation Office has run simulations of planets with different rotation speeds. A planet that spins too slowly can't generate enough Coriolis force to organise weather systems. The result is chaotic, unpredictable storms. A planet that spins too fast creates such strong winds that stable climates can't form. Earth's 24-hour rotation is nearly perfect. Long enough to distribute energy evenly, short enough to create organised circulation. It's one of the many Goldilocks factors that make our planet habitable. And then there's the Moon, our quiet companion, which plays a crucial role in stabilising Earth's rotation. Billions of years ago, a Mars-sized object called Theia collided with the young Earth. The impact was catastrophic, vaporising portions of both worlds. Debris from the collision spiralled into orbit and eventually coalesced into the Moon. That violent birth had a profound effect on Earth's rotation. The impact sent our planet spinning much faster, with days lasting only about 6 hours. But over billions of years, the Moon's gravity has been slowing Earth's spin through tidal forces. Here's how it works. The Moon's gravity pulls on Earth's oceans, creating 2 tidal bulges, one facing the Moon and one on the opposite side. As Earth rotates beneath these bulges, friction between the moving water and the seafloor acts like a brake, gradually slowing the planet's spin. At the same time, Earth's gravity pulls on the Moon, but because the Moon is already tidally locked, showing us the same face always, our planet transfers rotational energy to the Moon's orbit. The result? The Moon slowly drifts away, currently at about 1.5 inches per year, and Earth's days grow longer by about 1.7 milliseconds per century. ESA's Gaia mission has shown that this gravitational dance does more than change day length. It stabilizes Earth's axial tilt, the angle at which our planet leans as it orbits the Sun. That tilt, currently about 23.5 degrees, is what gives us seasons. Without the Moon's stabilizing influence, Earth's tilt would vary chaotically over thousands of years, swinging wildly from nearly 0 to over 85 degrees. Mars offers a cautionary tale. It has 2 tiny moons, Phobos and Deimos, but they're far too small to stabilize its axial tilt. As a result, Mars's tilt varies between 15 and 35 degrees over hundreds of thousands of years. During periods of extreme tilt, the poles receive direct sunlight, causing the polar ice caps to sublimate and creating temporary, intense climate changes. No life could adapt to such wild swings. Earth's stable tilt, maintained by the Moon, gives us predictable seasons. Spring follows winter, summer follows spring, year after year, for millions of years. Life has evolved like complex strategies to match these seasons: migration, hibernation, flowering, breeding cycles. Remove that stability and ecosystems would collapse. So rotation, combined with the Moon's gravitational influence, creates a climate stable enough for life to flourish over geological timescales. Let's look beyond Earth for a moment. How does rotation affect habitability on other worlds? Take Venus, Earth's sister planet. Venus is only slightly smaller than Earth, with a similar composition, yet it's a hellscape. Surface temperatures reach 900 degrees Fahrenheit, hot enough to melt lead. The atmosphere is crushing, 90 times thicker than Earth's, made mostly of carbon dioxide with clouds of sulfuric acid. But here's the strange part. Venus rotates incredibly slowly. One full rotation takes 243 Earth days, and it spins backward, the only planet in our solar system with retrograde rotation. Its day is actually longer than its year. Without rapid rotation, Venus couldn't generate a strong magnetic field. Its core likely stopped producing a dynamo long ago. Without magnetic protection, solar radiation bombarded the upper atmosphere for billions of years. Combined with runaway greenhouse warming, Venus lost any water it once had. Today, it's the hottest planet in the solar system, even hotter than Mercury despite being farther from the Sun. The slow rotation also means Venus has no Coriolis effect to speak of. Atmospheric circulation is driven entirely by temperature differences, creating a single massive convection cell that circles the planet. The thick atmosphere rotates much faster than the surface, racing around Venus in just 4 days. This superrotation is one of the great mysteries of planetary science. On the other end of the spectrum is Jupiter, the fastest spinning planet in our solar system. Despite being 11 times wider than Earth, Jupiter completes a full rotation in less than 10 hours. This rapid spin creates fierce atmospheric dynamics. Jet streams race around the planet at hundreds of miles per hour, and the Great Red Spot, a storm larger than Earth, has raged for at least 400 years, possibly much longer. Jupiter's rapid rotation also generates the strongest planetary magnetic field in the solar system, 20,000 times stronger than Earth's. This field traps charged particles, creating intense radiation belts that would be lethal to unprotected spacecraft. The lesson from these worlds is clear: rotation speed matters. Too slow, and you lose magnetic protection and atmospheric circulation. Too fast, and you create extreme weather and unstable conditions. Earth's 24-hour rotation sits in a sweet spot, fast enough to generate a protective magnetic field and organize weather patterns, but slow enough to allow stable climates. NASA's exoplanet research has extended this principle beyond our solar system. The James Webb Space Telescope and other instruments have detected thousands of exoplanets, and scientists are beginning to assess their habitability based in part on rotation. Many exoplanets orbit very close to their stars, completing orbits in just days or even hours. At such close range, tidal forces from the star gradually lock the planet's rotation to its orbit, just as the Moon is locked to Earth. These tidally locked planets always show the same face to their star, creating a permanent day-side and night-side. Computer models suggest that tidally locked planets might still support life, but only under certain conditions. If the atmosphere is thick enough, heat can be distributed from the day side to the night side, preventing extreme temperature differences. Winds would be fierce, driven by the temperature gradient, but stable climate zones might exist in the twilight regions between perpetual day and perpetual night. Some of the most promising exoplanet candidates, like those in the TRAPPIST-1 system, are likely tidally locked. Whether they could harbour life remains an open question, one that future telescopes may answer. Back on Earth, rotation doesn't just sustain life, it shapes the very structure of living organisms. The 24-hour cycle has become so fundamental that evolution has woven it into biology at every level. Consider plants. They don't just passively respond to light, they anticipate it. Studies have shown that plants begin preparing for dawn before the sun rises, adjusting their internal chemistry in advance. Genes switch on and off in daily rhythms, even when plants are kept in constant darkness. The rhythm persists, a molecular echo of rotation. Animals show even more sophisticated adaptations. Migratory birds time their journeys to match seasonal changes driven by Earth's tilt and rotation. Salmon return to their birthplace rivers with precision timing. Coral reefs synchronize mass spawning events to specific lunar phases, which themselves depend on the Moon's orbit and Earth's rotation. Humans, too, are creatures of rotation. Our sleep-wake cycles, body temperature fluctuations, hormone releases, even our cognitive performance all vary on a 24-hour schedule. Studies of people living in environments without natural light show that our internal clocks run slightly longer than 24 hours, usually about 24.2 hours, but they quickly synchronize when exposed to sunlight again. This synchronization is controlled by a tiny cluster of neurons in the brain called the suprachiasmatic nucleus, located in the hypothalamus. These neurons receive light signals from the eyes and coordinate the body's circadian rhythms. Damage to this region disrupts sleep, metabolism, and mood, demonstrating how deeply rotation is embedded in our biology. There's even evidence that rotation influences evolution itself. A 2019 study published in Nature Ecology and Evolution found that species diversity tends to be higher in regions with stable day-night cycles. The predictability of rotation creates ecological niches, allowing species to specialize in dawn hunting, nocturnal activity, or diurnal lifestyles. This temporal partitioning reduces competition and promotes biodiversity. Without Earth's rotation, the planet wouldn't just be uninhabitable because of climate and magnetic field loss, it would lack the temporal structure that life depends on. The rhythm of day and night is as essential as air and water, so when we ask whether spinning made life possible, the answer is a resounding yes. Rotation defines day length, which drives circadian rhythms. It generates magnetic fields, which protect atmospheres. It creates the Coriolis effect, which organizes weather and ocean currents. It stabilizes axial tilt through tidal interactions, which gives us seasons. Every level of habitability, from planetary scale down to cellular scale, depends on rotation. As astrophysicist Neil deGrasse Tyson once observed, "The universe is under no obligation to make sense to you. But remarkably, when we study its workings, we find that the conditions for life emerge naturally from the laws of physics. Rotation is one of those laws, not a coincidence, not a lucky accident, but a fundamental property of matter and energy that, when combined with the right planetary conditions, creates the possibility of life. Take a breath. Feel the stillness around you. But remember, you're on a spinning world, protected by invisible fields, warmed by a rotating star, moving through a galaxy that itself is turning. Every heartbeat, every breath, every thought is made possible by motion so smooth you can't feel it. Now, as we continue this journey, we arrive at something even stranger. Because rotation doesn't just make life possible. At extreme speeds, it begins to warp something even more fundamental than space. It begins to bend time itself. Part 4. When rotation bends time. There's a speed beyond which rotation stops being mere motion and becomes something else entirely. A threshold where spinning objects don't just move through space, they twist the fabric of space-time itself, pulling at the flow of time, bending it, warping it, making seconds stretch or compress depending on where you stand. This isn't science fiction, it's Einstein's general relativity, confirmed by decades of observation, and it means that time, the one thing we thought was absolute and universal, is actually fluid, malleable, shaped by rotation. Let me take you on a journey to the places where spin becomes so extreme that time itself begins to break. Einstein published his general theory of relativity in 1915, fundamentally changing our understanding of gravity. He showed that mass and energy don't just pull on objects through some mysterious force, they curve the geometry of space-time itself. Massive objects create dips and valleys in the fabric of reality, and other objects roll along those curves. But Einstein's equations revealed something even stranger. Rotation also curves space-time. When a massive object spins, it drags space-time around with it, creating a swirling vortex in the very structure of reality. This effect is called frame dragging, and it's one of the most beautiful and counterintuitive predictions of relativity. Imagine space-time as a vast, calm ocean. When Earth spins, it's like a marble turning in honey. The honey near the marble gets dragged along with it, swirling gently. In the same way, Earth's rotation drags space-time around the planet, creating a subtle twist in the flow of time and space. For decades, this remained theoretical. The effect is so tiny near Earth that detecting it seemed impossible. But in 2004, NASA launched Gravity Probe B, one of the most precise experiments in history. The spacecraft carried 4 gyroscopes, each a quartz sphere polished to near perfection, the smoothest object ever made by humans. These gyroscopes were placed in orbit 400 miles above Earth and allowed to spin freely in space. According to classical physics, they should have maintained their orientation precisely, pointing at the same distant star forever. But according to general relativity, Earth's rotation should drag space-time around the planet, causing the gyroscope's axis to drift ever so slightly. After a year of measurements, NASA physicist Francis Everett, who led the mission, announced the results. The gyroscopes had drifted by exactly the amount Einstein predicted, about 0.011 degrees per year. It's an almost imperceptible twist, but it's real. Earth's gentle spin, its once-per-day rotation, is powerful enough to bend the flow of time and space. Francis Everett described it beautifully. As Earth rotates, it drags space-time around with it, much like a spinning sphere twisting the honey in which it is immersed. If Earth, spinning relatively slowly, can do this, imagine what happens near objects with far more mass and far greater rotational speeds. Enter neutron stars. When a massive star, at least 8 times the mass of the Sun, exhausts its nuclear fuel, it can no longer support itself against gravity. The core collapses catastrophically. In less than a second, matter equivalent to the mass of our Sun compresses into a sphere only about 12 miles across. At such densities, protons and electrons are crushed together, forming neutrons. The result is a neutron star, an object so dense that a sugar cube-sized piece would weigh 1 billion tons on Earth. To conserve angular momentum, these collapsing stars spin faster as they shrink, just like a figure skater pulling in her arms. The result can be rotation speeds of hundreds of times per second. NASA's NICER instrument, aboard the International Space Station, has detected pulsars spinning up to 716 times per second. That's faster than a kitchen blender, but for an object with more mass than the Sun. These pulsars, rotating neutron stars with powerful magnetic fields, emit beams of radiation from their magnetic poles. As they spin, these beams sweep across space like lighthouse beams. When Earth happens to lie in the path of the beam, we detect regular pulses of radio waves, hence the name pulsar. The regularity is extraordinary. Some pulsars keep time more accurately than atomic clocks, their rotation slowing by only microseconds per year. They're cosmic metronomes, ticking with a precision that rivals our best technology. But near a pulsar, space-time is no longer calm. It's violently twisted. Frame dragging becomes extreme. The neutron star's rotation drags space-time around with such force that even light struggles to travel in straight lines. And time? Time near a pulsar runs noticeably slower than it does far away. This is gravitational time dilation, a direct consequence of both the star's mass and its rotation. If you could hover safely near a pulsar, an impossible feat, and watch a clock on Earth, you'd see it ticking faster than your own. For every second you experience, more time would pass elsewhere in the universe. This isn't speculation, it's measurable. Astronomers observing binary pulsars, pairs of neutron stars orbiting each other, can detect these time differences through subtle shifts in the pulse's timing. But if you want to see time truly break, you have to go to the most extreme rotators in the universe, spinning black holes. In 1963, mathematician Roy Kerr solved Einstein's equations for a rotating black hole. What he found was astonishing. A spinning black hole doesn't just have an event horizon, the point of no return beyond which nothing can escape. It also has something called an ergosphere. The ergosphere is a region outside the event horizon, where space-time itself is dragged around the black hole faster than the speed of light. In this region, nothing can remain stationary relative to distant space. Everything, matter, light, even space-time itself is forced to rotate with the black hole. It's as if space itself has become a river, flowing inexorably in one direction, and you're caught in the current. No matter how hard you try to stay still, you're carried along. Inside the ergosphere, time behaves in ways that seem impossible. The faster the black hole spins, the more extreme the effects. Near the maximum rotation speed allowed by physics, time can slow to almost nothing relative to the outside universe. This means that if you could survive near a rapidly spinning black hole, something currently beyond any technology, you could experience time passing slowly while the rest of the universe aged rapidly. You might experience an hour while centuries passed elsewhere. This isn't just theory. In 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole's shadow, the supermassive black hole at the center of galaxy M87. In 2022, they released an image of Sagittarius A, the black hole at the center of our own Milky Way galaxy. These images show glowing rings of superheated gas orbiting the black holes at tremendous speeds. The light from this gas is bent and delayed by the curvature of spacetime, creating the bright arcs we see. Some of that light has been trapped briefly near the black hole, delayed by the warping of time before finally escaping. NASA's Chandra X-ray Observatory and other instruments have measured the rotation speeds of these black holes by analysing how matter spirals inward. Sagittarius A, for example, appears to be spinning at a moderate rate, about 10–20% of the maximum possible speed. M87's black hole spins even faster, approaching half the maximum. At those speeds, the effects on time are significant. Matter falling toward the black hole experiences severe time dilation. From our perspective, it seems to slow down, freeze, and fade as it approaches the event horizon, eternally falling but never quite crossing over. From the perspective of the infalling matter, it crosses quickly, but time outside rushes forward at extraordinary rates. The mathematics is mind-bending, but the observations confirm it. Rotation and gravity together create a landscape of time where the past, present and future lose their fixed meaning. Even here on Earth, in our everyday lives, time dilation from rotation is real and measurable. GPS satellites orbit Earth at altitudes of about 12,550 miles, travelling at approximately 8,700 miles per hour. At those speeds and altitudes, they experience both special relativistic time dilation, due to their velocity, and general relativistic time dilation, due to Earth's weaker gravitational field at higher altitudes. The combined effect is about 38 microseconds per day. That might sound trivial, but GPS relies on precise timing. Signals from satellites travel at the speed of a light, and even a tiny timing error translates to position errors of several miles. To compensate, GPS satellites have their clocks deliberately set to run slightly slower before launch. Once in orbit, the relativistic effects cause them to tick at exactly the same rate as clocks on Earth's surface. Without this correction, GPS would become useless within hours. Every time you use your phone's map, every time you navigate using GPS, you're relying on corrections for time dilation caused by rotation and gravity. Einstein's equations aren't abstract. They're embedded in the technology we use daily. Even more fascinating, your head ages faster than your feet. Because your head is slightly farther from Earth's centre, it experiences slightly weaker gravity and slightly faster rotation. Time passes infinitesimally faster for your brain than for your toes. Over a lifetime, the difference is only about 90 nanoseconds, far too small to notice, but real. Atomic clocks are precise enough to measure this. In 2010, physicists at the National Institute of Standards and Technology placed two atomic clocks at different heights, one just 12 inches above the other. The higher clock ran measurably faster, exactly as Einstein predicted. Raise a clock by a single foot and time speeds up. This means that living at higher altitudes where gravity is weaker, you age ever so slightly faster than someone at sea level. Over decades, the difference might be a few microseconds, but again, It's real and measurable. Rotation and gravity don't just affect how we measure time, they affect time itself. Time is not a universal constant ticking away the same for everyone. It's a local phenomenon shaped by motion, mass, and spin. As theoretical physicist Kip Thorne, who consulted on the film Interstellar, explained, "In the warped space-time near a spinning black hole, the future of one observer can become the past of another. Rotation doesn't just bend trajectories, it bends the sequence of events, the very rhythm of existence. This leads to one of the strangest predictions in all of physics, closed time-like curves. In certain extreme solutions to Einstein's equations, particularly around rapidly rotating black holes or other exotic objects, it becomes mathematically possible for a particle to travel through space-time and arrive back at its own starting point in space and time. In other words, time travel to the past. Whether these solutions represent physical reality or mathematical, curiosities is still debated. Most physicists believe that quantum effects or other principles would prevent such paradoxes, but the fact that rotation can even raise the possibility shows how profoundly it affects the structure of reality. Even on scales we can observe, rotation's effects on time are dramatic. The James Webb Space Telescope has observed quasars, supermassive black holes actively feeding at the centres of distant galaxies. The light from these objects is stretched and redshifted, partly because the universe is expanding, but also because time runs slower in the intense gravitational fields near the black holes. Some of the light JWST detects left those spinning giants over 13 billion years ago, when the universe was less than 1 billion years old. We're seeing light that has travelled across cosmic time, stretched and delayed by the rotation and gravity of black holes billions of times more massive than our Sun. Frame dragging, time dilation, warped space-time, these aren't abstract concepts. They're the universe showing us that reality is far stranger and more beautiful than our everyday experience suggests. Take a slow, deep breath. Right now, at this moment, your experience of time is being gently shaped by Earth's rotation. The planet spins beneath you, dragging space-time along with it, creating a subtle asymmetry in the flow of seconds. You live in a universe where time is not fixed, where rotation can bend the very fabric of existence. And if rotation can bend time, the next question becomes inevitable. If spin controls how time flows, what controls the spin itself? Who or what keeps the cosmic clocks ticking? That's the mystery waiting in our next chapter. Part 5. What controls the cosmic clocks? Every second of your life is defined by rotation. The ticking of a clock, the rhythm of your heartbeat, the cycle of day and night, all are manifestations of spin at different scales. From the quantum whirl of electrons to the stately orbit of galaxies, rotation is the universe's timekeeper. But here's the profound question. If spin controls time, what controls spin? The answer takes us to the most precise instruments humanity has ever built, and then beyond to the deepest laws of physics. Let's start small. What is a second? For most of history, a second was defined by Earth's rotation. One day was divided into 24 hours, each hour into 60 minutes, each minute into 60 seconds. A second was simply 186,400th of a day. But there was a problem. Earth's rotation isn't perfectly constant. Tidal forces from the moon slow it gradually. Earthquakes can shift mass, slightly altering the rotation speed. Even seasonal changes in ice distribution at the poles create tiny variations in day length. By the mid-20th century, scientists needed something more stable. They found it in atoms. In 1967, the International Bureau of Weights and Measures redefined the second based on atomic physics. Specifically, it's defined by the cesium-133 atom, 1. Second is now exactly 631,170 oscillations of the radiation corresponding to the transition between two hyperfine levels of cesium relativity ground state. That's a mouthful, but what it means is beautiful. A second is no longer defined by the rotation of Earth, a planet gradually slowing. It's defined by the internal rotation of an atom, by quantum spin. Inside an atom, electrons exist in specific energy levels, like rungs on a ladder. When an electron jumps from one level to another, it emits or absorbs a photon of light with a precise frequency. That frequency is determined by the electron's quantum properties, including spin. Cesium-133 was chosen because its atomic transitions are extraordinarily stable. Build two identical cesium atomic clocks, and they'll keep time in perfect synchrony, drifting by only 1 second every 100 million years. Today's best atomic clocks, using strontium or ytterbium atoms, are even more precise. They take longer than the age of the universe to drift by a single second. These clocks are so stable that they can detect time dilation from height differences of just 1 centimetre. So in the deepest sense, the flow of time as we measure it is governed by atomic spin. The quantum rotation of particles, a property so fundamental it cannot be broken down further, defines the seconds we live in. But atomic clocks still depend on Earth's rotation for context. We sync our atomic time with the planet's spin using a system called leap seconds. Because Earth's rotation is slowing, atomic time gradually drifts ahead of solar time. About every 18 months on average, scientists at the International Earth Rotation and Reference System Service add a leap second to keep our clocks aligned with the planet's actual rotation. It's a small adjustment, but it reveals something profound. Human timekeeping is a compromise between the ancient rhythm of planetary spin and the quantum precision of atomic spin. If we compare clocks at different locations on Earth, we find that time itself varies depending on rotation and gravity. At the equator, where Earth's surface moves fastest, clocks run slightly slower due to both velocity-based time dilation and the slightly stronger centrifugal effect reducing effective gravity. At the poles, where rotation is minimal but gravity is slightly stronger, clocks run at a different rate. The differences are tiny, measured in nanoseconds per day, but they're real. GPS satellites must account for these variations constantly, adjusting their timing signals based on their orbital speed and altitude. Even more fascinating, experiments have placed atomic clocks on airplanes and flown them around the world. When compared to stationary clocks on the ground, the flying clock showed measurable time differences exactly as Einstein predicted. Flying eastward, in the same direction as Earth's rotation, the clocks experienced more speed and thus ran slightly slower. Flying westward, against Earth's rotation, they ran slightly faster. These aren't thought experiments, they're real measurements, proving that rotation directly affects time. Now let's zoom out. What keeps planets spinning? The answer is conservation of angular momentum, one of the most fundamental laws in physics. In a closed system, where no external torque is applied, angular momentum remains constant. When the solar system formed 4.6 billion years ago from a collapsing cloud of gas and dust, that cloud had a small amount of rotation. As it collapsed under gravity, it spun faster, just like a figure skater pulling in her arms. This rotation flattened the cloud into a disk, with the sun forming at the centre and planets coalescing from the remaining material. Each planet inherited some of that original angular momentum, and because space is nearly a perfect vacuum with almost no friction, they've continued spinning for billions of years without slowing significantly. Yes, tidal forces gradually transfer angular momentum between planets and their moons, and between planets and the Sun. But the total angular momentum of the solar system remains constant. What one object loses, another gains. This principle extends to every scale. Galaxies, star systems, even atoms all obey conservation of angular momentum. Spin is never created or destroyed, only transferred. So in a sense, no one controls the spin. Once set in motion, the universe keeps spinning because the laws of physics require it. But where did that initial spin come from? Trace it back far enough, and you arrive at the Big Bang and the quantum fluctuations that filled the early universe. Those fluctuations, amplified by cosmic inflation, carried tiny amounts of angular momentum. As matter clumped together under gravity, that momentum was preserved and amplified. The universe doesn't need a hand to keep it spinning. The first spin was enough. Angular momentum has been conserved ever since, flowing from primordial quantum fields to galaxies, from galaxies to stars, from stars to planets, from planets to atoms, and from atoms to the ticking of our most precise clocks. In 2016, ESA's Gaia mission mapped the motions of over 1 billion stars in the Milky Way. The data revealed that our galaxy rotates once every 230 million years, a period astronomers call a galactic year. The last time our solar system was in this position, dinosaurs were just beginning to dominate Earth. Every star in the galaxy contributes to this grand rotation, orbiting the galactic center in a vast, slow spiral. The Sun moves at about 514,000 miles per hour on its galactic orbit, carrying Earth and the other planets along with it. This motion has been constant for billions of years, powered by nothing more than the angular momentum inherited from the galaxy's formation. No engine is needed, no force maintains it. It simply is, a continuation of motion that began when gravity first gathered the Milky Way's matter from the cosmic void. Even the Sun itself spins, rotating once every 27 days at its equator. But the Sun isn't a solid body, it's a ball of plasma, and different parts rotate at different speeds. The equator completes a rotation in 25 days, while the poles take about 35 days. This differential rotation twists the Sun's magnetic field into complex shapes, creating sunspots, flares, and coronal mass ejections. That magnetic activity affects Earth directly. When a solar flare erupts, charged particles stream toward our planet, interacting with the magnetosphere and sometimes disrupting satellites and power grids. The Sun's rotation, its internal spin, shapes the space weather that surrounds us. So when we ask what controls spin, the answer is layered. At the quantum level, spin is an intrinsic property of particles, fundamental and unchangeable. At the atomic level, the arrangement of electron spins creates the precise frequencies we use to define time. At planetary scales, spin is maintained by conservation of angular momentum, inherited from the solar system's formation. At galactic scales, rotation emerges from the gravitational collapse of matter, a slow dance billions of years old. And at the cosmic scale, the universe itself may carry a faint memory of rotation from its earliest moments, a twist in space-time that cascades across billions of light years. Everything that moves measures. Everything that measures moves. Time isn't separate from motion. It's defined by it, shaped by it, inseparable from the great cosmic rotation that began 13.8 billion years ago and continues today. As NASA's Jet Propulsion Laboratory elegantly states, the laws of motion don't change. The universe runs on balance. What is lost in one place is gained in another. There's no master clock, no hidden hand. The very act of motion maintains its own timing. Take a breath. The atoms within you spin in harmony with the turning Earth, the orbiting moon, the spiraling galaxy. You're already part of that motion. Every heartbeat is a fraction of a universal rhythm that began long before clocks, long before calendars, long before life itself. And as this rhythm continues, as the universe spins through the darkness, another question quietly rises. A question about balance, about perfection, and about the tiny imperfections that made everything possible. Because if the universe depends on perfect symmetry, perfect balance, how did anything ever begin? Why didn't it simply remain frozen, unchanging, eternal? The answer lies in a crack, a flaw, a beautiful asymmetry that set everything in motion. That's where we drift next. Part 6. The crack in perfection, how broken symmetry created everything. Imagine a perfectly balanced universe, every force equal and opposite, every particle matched with its mirror, every direction in space equivalent to every other. No preferred spin, no favoured orientation, complete and utter symmetry. In such a universe, nothing would happen. Ever. There would be no motion because motion requires imbalance, a difference, a reason for energy to flow from here to there. There would be no structure because structure requires some regions to be denser than others. There would be no time because time requires change, and in perfect symmetry, nothing can change. But our universe is not perfectly symmetric. It's close, remarkably close, but not quite. And that tiny imperfection, that subtle crack in the mirror, is why you exist, why anything exists. Tonight, we're going to explore the most profound asymmetries in nature, the broken symmetries that gave birth to matter, motion, and time itself. Let's start at the beginning, in the first fractions of a second after the Big Bang. According to the standard model of particle physics, the early universe was unimaginably hot and dense, filled with a soup of fundamental particles and energy. At that temperature, the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single force. But as the universe expanded and cooled, something remarkable happened. The forces began to separate, like oil and water unmixing. This process is called spontaneous symmetry breaking, and it shaped everything from the structure of atoms to the fabric of space-time itself. The first symmetry to break was gravity, separating from the other forces within the first 10⁻43 seconds, the Planck time. Then, in stages, the strong nuclear force separated, followed by the electromagnetic and weak forces. Each time a symmetry broke, the universe became more complex. Particles gained mass. Forces gained distinct properties. The smooth, uniform energy of the early universe crystallized into the diverse structures we see today. But the most important symmetry breaking, the one that makes your existence possible, happened when matter outnumbered antimatter. In the first microseconds after the Big Bang, matter and antimatter were created in equal amounts. For every quark, there was an antiquark. For every electron, a positron. These pairs would collide and annihilate, converting back into pure energy. If this balance had been perfect, all matter and antimatter would have destroyed each other, leaving only a universe filled with light. No atoms, no stars, no planets, no life. But the balance wasn't perfect. For every billion antimatter particles, there were 1,000,000,001 matter particles. That tiny excess, just 1 part in 1,000,000,000, survived the annihilation. That leftover matter became everything we can see. Every star, every galaxy, every atom in your body. This asymmetry is called Baryon asymmetry, and it's one of the great mysteries of cosmology. Why did the universe prefer matter over antimatter? The first clue came in 1964 when physicists James Cronin and Val Fitch discovered CP violation, a subtle difference in how certain particles and their antimatter partners behave. They were studying neutral kaons, strange particles that can transform between matter and antimatter, states. They found that kaons and antikaons don't transform at exactly the same rates. The universe has a slight preference for matter. This discovery earned Cronin and Fitch the Nobel Prize in 1980. But it only partially solved the mystery. The amount of CP violation they observed isn't enough to explain the matter-antimatter imbalance we see. There must be other sources of symmetry breaking we haven't discovered yet. Today, experiments at CERN's Large Hadron Collider are studying the Higgs boson and other particles, searching for additional sources of CP violation. They're trying to answer one of the most fundamental questions in physics. Why does the universe prefer one kind of matter over its mirror image? The Higgs boson itself is a product of symmetry breaking. In the first trillionth of a second after the Big Bang, when the universe cooled below a critical temperature, something called the Higgs field gained a non-zero value everywhere in space. Before this moment, all particles were massless, zipping around at the speed of light. But when the Higgs field activated, it created resistance. Particles that interact with the Higgs field gain mass, while those that don't, like photons, remain massless. It's often compared to walking through water. Someone who doesn't interact with water can move freely. But someone who does feels resistance, inertia, weight. The Higgs field is like an invisible ocean filling all of space, and mass is the drag particles experience moving through it. This symmetry breaking locked the universe into its current form. Particles gain distinct masses, forces gain distinct strengths, and the rich tapestry of chemistry and biology became possible. But symmetry breaking isn't just about particles. It affects space-time itself. The cosmic microwave background mapped by ESA's Planck satellite and NASA's WMAP mission reveals tiny temperature fluctuations across the sky. These represent density variations in the early universe, regions that were slightly denser or less dense than average. Without these variations, gravity would have had nothing to work with. The universe would have remained smooth and uniform forever, a thin, expanding gas with no structure. But with these tiny asymmetries, gravity could amplify them. Dense regions attracted more matter, becoming denser still, eventually collapsing into galaxies and stars. These fluctuations trace back to quantum randomness during cosmic inflation. In the first fraction of a second, quantum fluctuations, tiny uncertainties allowed by Heisenberg's uncertainty principle, were stretched to cosmic scales by inflation's exponential expansion. What began as quantum randomness became the seeds of galaxies. The universe's largest structures owe their existence to the smallest possible imperfections. Even the arrow of time, the fact that time flows from past to future, may be a consequence of broken symmetry. In physics, most fundamental laws are time-symmetric. The equations work equally well forward or backward. If you filmed electrons colliding and played the video in reverse, you couldn't tell the difference. The laws of physics would look the same, but thermodynamics, the science of heat and energy, isn't time-symmetric. Entropy always increases. Systems move from order to disorder, never the reverse. Hot coffee cools, broken eggs don't spontaneously reassemble. Time has a direction. Physicist Sean Carroll has argued that the arrow of time emerges from the universe's initial low-entropy state. At the Big Bang, the universe was in an extraordinarily ordered configuration, all energy concentrated in a tiny volume, perfectly smooth on large scales except for those quantum fluctuations. As the universe expanded, entropy increased. energy spread out, structures formed and then decayed. The increase in entropy gives time its direction, its flow from past to future. And that initial low entropy state? It may be the ultimate broken symmetry, the cosmic asymmetry that allows time itself to exist. Even on smaller scales, asymmetry appears everywhere in nature. Consider galaxies. When astrophysicist Lyosha Mir analysed hundreds of thousands of spiral galaxies, he found they don't rotate randomly. There's a slight but measurable preference for one direction over another in different parts of the sky. This large-scale asymmetry might trace back to the early universe's spin, a relic rotation imprinted during the Big Bang. Or consider neutrinos, the ghostly particles that pass through matter almost without interacting. Every neutrino in the universe is left-handed, meaning its spin is always oriented opposite to its direction of motion. There are no right-handed neutrinos, at least none we've ever detected. This handedness, called chirality, is built into the weak nuclear force. The universe simply prefers one spin orientation over the other at the quantum level, and this brings us to one of the most beautiful and mysterious asymmetries, the handedness of life itself. Every living thing on Earth uses left-handed amino acids and right-handed sugars. These molecules come in mirror image pairs, like your left and right hands, but life exclusively uses one form. In the lab, when you synthesize amino acids from scratch, you get equal amounts of left and right-handed versions. There's no chemical reason to prefer one over the other, yet every protein in your body is built from left-handed amino acids. If you tried to build a protein from right-handed amino acids, it wouldn't work. The shape would be wrong, the chemistry incompatible with life. Why this asymmetry? One possibility is that it's random. Life started with one form by chance, and evolution locked it in. Once biochemistry committed to left-handed amino acids, switching would have been impossible. But there's another, more intriguing possibility. The asymmetry may have come from space. In 1969, the Murchison meteorite fell in Australia. Analysis revealed over 70 different amino acids, and remarkably there was a slight excess of left-handed forms. Not much, just a few percent more left than right, but it was there. NASA's studies of interstellar chemistry have found that circularly polarized ultraviolet light from young stars can selectively destroy one form of amino acid more than the other. Over millions of years in space, this could create an imbalance. When those biased molecules arrived on early Earth via meteorites and comets, they may have seeded life with a preferred handedness. Life didn't choose left-handed amino acids randomly. The universe chose for us, through the spin of starlight in molecular clouds billions of years ago. This means the asymmetry in your body, the twist in every protein, might trace back to the same broken symmetries that gave birth to matter, structure, and time. Even the magnetic field of Earth shows this pattern. The field has a north and south pole, a clear directionality. Every few 100,000 years, the field flips, reversing polarity. The north magnetic pole becomes south, and vice versa. These reversals are recorded in rocks as they form, magnetic minerals aligning with the field and freezing that orientation into stone. Geologists studying ancient lava flows have mapped these reversals going back millions of years. The pattern is irregular, chaotic even, but always directional. The field never loses its asymmetry, its preference for one orientation over another. All of this, from the matter-antimatter imbalance to the handedness of amino acids, from the arrow of time to the spin of galaxies, emerges from the same principle. Perfect symmetry is sterile. Imperfection creates. As theoretical physicist Murray Gell-Mann once said, if the world were perfectly symmetrical, there would be nothing. It's the deviations, the slight differences that make reality possible. The universe began with near-perfect symmetry, and then, through a series of gentle breakings, became complex enough to support stars, planets, chemistry, and life. You exist because of a flaw, a beautiful, necessary flaw. The cosmic microwave background's temperature variations, those tiny ripples, represent the first visible asymmetry. From them, everything else followed. Galaxies, stars, planets, oceans, forests, consciousness. All from a pattern of imperfection so subtle, it's barely detectable, yet so profound it created everything. ESA's Planck satellite also detected subtle polarization in the CMB, swirls in the ancient light called B-modes. If confirmed as primordial signals, these would be direct evidence of gravitational waves from inflation, ripples in space-time itself from the universe's first violent expansion. These swirls would prove that space-time was twisted, asymmetric, spinning from the very beginning. Take a slow breath. Your existence is an echo of that first asymmetry. The atoms in your body are the leftover matter from an imperfect annihilation. The direction of time you experience flows from an initial state of broken symmetry. Even the molecules that build your cells carry a twist, a handedness that may have originated in the polarized light of ancient stars. You're not an accident in a perfect universe. You're the inevitable consequence of a universe that dared to be imperfect. And that imperfection continues to shape everything. Because if broken symmetry created the universe, it also creates the structures that hold it together, the invisible scaffolding that keeps galaxies from flying apart. That's where we turn next, to the dark matter that binds the cosmos, and the mystery of how invisible rotation shapes everything we see. Part 7. The Invisible Rotation. How dark matter holds galaxies together. Look up at the night sky. Every star you see, every glowing nebula, every distant galaxy, all of it together represents only 5% of the universe. The rest is hidden. 27% is dark matter, invisible substance that doesn't emit, absorb, or reflect light. 68% is dark energy, a mysterious force accelerating the universe's expansion. We live in a cosmos where 95% of everything is unseen, and without that invisible majority, particularly dark matter, galaxies couldn't exist. They would spin themselves apart, their stars flung into the void. The story of dark matter begins with a mystery. Galaxies spin too fast. In the 1930s, Swiss astrophysicist Fritz Zwicky studied the Coma Cluster, a massive collection of over 1,000 galaxies located about 320 million light-years from Earth. He measured how fast the galaxies were moving relative to each other and calculated how much mass would be needed to hold them together gravitationally. The results shocked him. The visible matter, all the stars and gas, wasn't nearly enough. The galaxies were moving so fast they should have escaped the cluster's gravity billions of years ago. Yet there they were, bound together. Zwicky proposed something radical. There must be unseen mass, what he called dunkel Materie, dark matter, providing the additional gravity. For decades, his idea was largely ignored. But in the 1970s, American astronomer Vera Rubin revived it with even more compelling evidence. Rubin studied spiral galaxies, measuring the rotation speeds of stars at different distances from the galactic center. According to Newton's laws and Kepler's laws of orbital motion, stars farther from the center should orbit more slowly, just like outer planets in our solar system move slower than inner planets. But that's not what Rubin found. Using the Kitt Peak National Observatory, she discovered that stars far from galactic centers were orbiting just as fast as those near the core. The rotation curves were flat, not declining as expected. This was impossible unless there was additional mass extending far beyond the visible edge of each galaxy, unseen matter providing extra gravitational pull. Rubin's work, built on earlier observations by astronomer Ken Freeman and others, provided undeniable evidence. Galaxies are embedded in halos of dark matter, invisible spheres of mass extending hundreds of thousands of light years beyond the visible stars. And here's the crucial part. This dark matter rotates. Just like visible matter, dark matter carries angular momentum. When galaxies form, dark matter halos collapse and spin, creating whirlpools of invisible mass that guide the formation and rotation of visible galaxies. Computer simulations from NASA's Goddard Space Flight Center and other institutions have modeled how dark matter halos evolve. They show that without rotation, dark matter would simply clump symmetrically, unable to support the flat spinning disks of spiral galaxies we observe. But with rotation, dark matter forms extended halos that stabilize galactic disks, allowing stars to orbit safely at high speeds without being flung into intergalactic space. Think of it like a merry-go-round. If you spin faster and faster, you feel a stronger outward force trying to throw you off. You need to hold on tighter, or the structure needs to be stronger to keep you in place. Galaxies are cosmic merry-go-rounds. Stars orbit at hundreds of kilometers per second. Without something holding them, the centrifugal effect would scatter them. Dark matter is that something, an invisible grip keeping everything together. The evidence for dark matter extends beyond rotation curves. One of the most striking proofs comes from gravitational lensing. Einstein's general relativity predicts that mass bends spacetime, and light follows those curves. When light from a distant galaxy passes near a massive object, its path bends, just like light bending through a lens. If the lensing mass is large enough, it can magnify and distort the background galaxy into multiple images or graceful arcs. This is called strong gravitational lensing, and it allows astronomers to map the distribution of mass, including dark matter, in galaxy clusters. The European Space Agency's Hubble Space Telescope has captured stunning images of lensing. In some cases, the visible matter, the galaxies and hot gas, doesn't align with the lensing signal. The mass is somewhere else, invisible, but undeniably present. The most famous example is the Bullet Cluster, observed in 2006. Two galaxy clusters collided, passing through each other. The hot gas, visible in X-rays from NASA's Chandra Observatory, lagged behind, slowed by friction during the collision. But when astronomers mapped the mass distribution using gravitational lensing, they found that most of the mass had passed straight through, unaffected by the collision. That mass was dark matter, interacting only through gravity, not friction. The separation between visible matter and invisible mass was clear, direct evidence that dark matter is a distinct component of the universe, not just a misunderstanding of gravity. So, what is dark matter? Despite decades of research, we still don't know. The leading candidates are WIMPs, weakly interacting massive particles, hypothetical particles that interact only through gravity and the weak nuclear force. They'd be heavy, perhaps 10 to 100 times the mass of a proton, but incredibly elusive. Experiments like Xenon 1T in Italy and Lux Zeppelin in South Dakota have searched for WIMPs by placing ultra-sensitive detectors deep underground, shielded from cosmic rays. They're looking for the rare event when a dark matter particle collides with an atomic nucleus, producing a tiny flash of light or heat. So far, no confirmed detections, but the search continues. Another candidate is the axion, a much lighter particle predicted by theories attempting to solve other problems in physics. Axions would be produced in vast numbers in the early universe and could make up dark matter through sheer abundance rather than individual mass. Or dark matter could be something entirely unexpected, a form of matter we haven't even theorized yet. What we do know is that dark matter has mass, it gravitates, and it rotates, and its rotation is essential to the structure of the universe. NASA's James Webb Space Telescope is now observing the earliest galaxies, formed less than 400 million years after the Big Bang. Even at that young age, these galaxies show organized rotation and stable structures. That means dark matter halos were already in place, spinning, providing the gravitational framework for star formation. The universe didn't wait billions of years to organize. Dark matter began spinning almost immediately, shaping the cosmos from the very beginning. ESA's Euclid mission, launched in 2023, is mapping the three-dimensional distribution of galaxies across billions of light years. By studying how galaxies cluster and how their light is lensed, Euclid will create the most detailed map of dark matter ever made. The goal is to understand not just where dark matter is, but how it evolved, how its rotation and distribution changed over cosmic time. On galactic scales, dark matter doesn't just hold things together, it guides evolution. When two galaxies collide and merge, their dark matter halos interact, redistributing angular momentum. The result is often a slower, more elliptical galaxy, its spiral arms disrupted and scattered. Our own Milky Way is on a collision course with the Andromeda Galaxy. In about 4 billion years they'll merge. Computer simulations show that the collision will scatter stars, trigger bursts of star formation, and eventually settle into a single massive elliptical galaxy. During the merger, the dark matter halos will pass through each other, barely interacting except through gravity. But that gravitational interaction will reshape both galaxies, slowing their rotation and redistributing their matter. Dark matter even affects us more locally. The Milky Way's dark matter halo extends far beyond the visible disk, perhaps 600,000 light-years or more. Our solar system, orbiting 26,000 light-years from the galactic center, sits within this halo. That means dark matter is passing through the solar system, through Earth, through you, constantly. Billions of dark matter particles stream through your body every second, interacting with nothing, undetectable, ghost-like. It's an eerie thought. We live immersed in an invisible ocean of matter that outweighs everything we can see, yet we can't feel it, see it, or touch it. Only its gravity reveals its presence. The rotation of dark matter halos has one more crucial effect. It determines the rate at which galaxies form stars. Too much angular momentum, and gas can't fall inward to form stars. Too little, and galaxies collapse too quickly, creating bursts of star formation that exhaust the gas supply. The balance, tuned by dark matter's rotation, allows galaxies like the Milky Way to form stars steadily over billions of years, creating the long-lived stable environments where planets and life can develop. As astrophysicist Neil deGrasse Tyson observed, dark matter is the greatest cosmic mystery of our time, a shadow universe holding ours in its grip. Take a breath. Right now, you're held in place not just by Earth's gravity, but by the invisible rotation of the Milky Way's dark matter halo, a structure so vast it dwarfs everything you can see, yet spins silently, unseen, essential. And that invisible rotation does something even more remarkable. It may have shaped the direction of a life itself, down to the molecular level. Because if dark matter's spin influences galaxies, could it also have influenced the chemistry that created you? That's the question waiting in our next chapter, where we explore whether the universe's rotation decided which way life would twist. Part 8. The twist in life's molecules. There's a hidden asymmetry in every living thing, a subtle twist built into the molecular machinery of life. Your DNA spirals to the right. The amino acids that form your proteins bend to the left. This handedness, this molecular spin, is universal to all life on Earth. It's called chirality, from the Greek word for hand, and it's one of biology's deepest mysteries. Because there's no obvious chemical reason why life should prefer one direction over the other. In the lab, both forms are equally likely. Yet in nature, life chose, and that choice may have been made not by biology, but by the cosmos itself. Tonight we're going to trace the origin of life's twist back through chemistry, through starlight, through interstellar space to the very spin of galaxies. Let's start with a simple question. What is chirality? Imagine your hands. They're mirror images of each other, but you can't align them perfectly. Your left hand will never fit into a right-handed glove. That's chirality. It's the property of being non-superimposable on your mirror image. Many molecules have this property. They come in two forms, left-handed and right-handed, chemically identical but geometrically different. In chemistry, these are called enantiomers. For most molecules, chirality doesn't matter, but for life, it matters absolutely. Biological molecules must fit together with extraordinary precision, like keys in locks. A left-handed key won't open a right-handed lock, no matter how similar they are. Every amino acid except glycine, the simplest one, has chirality. In the lab, when you synthesize amino acids from non-biological sources, you get a 50-50 mixture of left and right forms called a racemic mixture. But life uses only left-handed amino acids, exclusively. Every protein in your body, every enzyme, every antibody is built from L amino acids. If you tried to build a protein from right-handed D amino acids, it wouldn't fold correctly. It wouldn't function. Your body would reject it. Similarly, the sugars that form the backbone of DNA and RNA are all right-handed. D-ribose and D-deoxyribose, never left-handed. This universal handedness must have been established very early, perhaps at life's origin 3.8 billion years ago. Once biochemistry committed to one form, switching became impossible. Too many molecules depended on the specific shapes. Evolution locked in the choice. But why that choice? Why left-handed amino acids and right-handed sugars, not the reverse? For decades, scientists thought it might be random. Life started with one form by chance, perhaps in a single lucky tide pool, and that form spread to all subsequent life. If we could rewind Earth's history and play it again, life might choose the opposite handedness. But evidence is mounting that the choice wasn't random at all. It came from space. In 1969, the Murchison meteorite fell in Victoria, Australia. It's a carbonaceous chondrite, a primitive meteorite containing organic compounds from before the solar system formed. When scientists analysed it, they found over 70 different amino acids. Some were common on Earth, but many were not, amino acids never found in terrestrial life. And here's the stunning part. When they measured the ratio of left to right-handed forms, they found a slight excess of left-handed amino acids. Not much, just a few percent, but it was there and it was real. This was the first evidence that handedness bias could come from space, from processes that occurred before Earth even existed. Subsequent studies of other meteorites confirmed the pattern. The Tagish Lake meteorite, which fell in Canada in 2000, and the Murray meteorite also showed left-handed excesses in certain amino acids. How could meteorites, lifeless rocks, develop a chiral preference? The answer may lie in polarized light. Light is an electromagnetic wave oscillating in a particular plane. Usually light from the sun or most other sources is unpolarized. oscillating equally in all directions, but under certain conditions light can become circularly polarized, rotating like a corkscrew as it travels. In star-forming regions where new stars are born inside massive clouds of gas and dust, intense ultraviolet light interacts with magnetic fields and dust grains. This interaction can create circularly polarized UV radiation. Studies by NASA's Astrobiology Institute and Ames Research Center have shown that circularly polarized UV light can selectively destroy one enantiomer of an amino acid more than the other. If left-handed light destroys right-handed amino acids more efficiently, you're left with an excess of left-handed forms. Over millions of years in interstellar space, this process could create a significant imbalance, perhaps 10–20% more of one form than the other. When those biased molecules arrive on planets via meteorites and comets, they seed the prebiotic chemistry that leads to life. This means the handedness of life may have been determined by starlight, by the polarization of UV radiation in molecular clouds, by the spin of magnetic fields around young stars. ESA's Rosetta mission provided supporting evidence. When the Philae lander touched down on Comet 67P Churyumov-Gerasimenko in 2014, it detected complex organic molecules including glycine, the simplest amino acid, and phosphorus-bearing compounds, essential for life. Analysis of the comet's materials suggested that these molecules formed in interstellar space and survived the comet's journey into the inner solar system. If those molecules carried a chiral bias, they would have delivered it to any planet they struck. Earth's early history was violent. For the first 500 million years, the planet was bombarded by asteroids and comets, a period called the Late Heavy Bombardment. These impacts delivered water, organic compounds, and perhaps the chiral bias that life would inherit. But the story goes deeper. The polarization of starlight itself may trace back to galactic rotation. In 2011, astrophysicist Lior Shamir analysed over 15,000 spiral galaxies and found a subtle preference in their rotation directions. Galaxies in one hemisphere of the sky tended to rotate clockwise more often, while those in the opposite hemisphere prefer counterclockwise. If the universe has a large-scale rotational structure, a remnant spin from the Big Bang, it could create preferred magnetic field orientations across vast regions of space. Those magnetic fields would shape how starlight becomes polarized, and that polarized light would determine the handedness of molecules in interstellar clouds, which would seed planets, which would give rise to life with a preferred molecular twist. It's a chain of causation stretching from cosmology to chemistry, from the spin of the universe to the spiral of DNA. Neutrinos provide another clue. These ghost-like particles, which barely interact with matter, all have left-handed chirality. Every neutrino in the universe spins counterclockwise relative to its direction of motion. There are no right-handed neutrinos, or if they exist, they don't interact with ordinary matter. This fundamental asymmetry is built into the weak nuclear force, one of the four fundamental forces. The universe, at its deepest level, has a handedness preference. In 1956, physicist Chen-Xiong Wu proved this through an elegant experiment. She cooled cobalt-60 atoms to near absolute zero and aligned their spins with a magnetic field. When the atoms underwent beta decay, emitting electrons, she found that more electrons flew out in one direction than the other. This violated parity symmetry, the assumption that physics should work the same way if you mirror flip everything. Wu's experiment showed that the weak force does not respect parity. Nature has a preferred handedness even at the quantum level. If the fundamental forces are chiral, it's not surprising that chemistry and biology inherit that bias. The universe's asymmetry cascades down through every scale, from particle physics to biochemistry. Even on Earth, The Coriolis effect creates rotational preferences. In the northern hemisphere, hurricanes spin counterclockwise. In the southern hemisphere, clockwise. The direction is determined by Earth's rotation beneath the storm. While this effect is far too weak to influence molecular chirality directly, it shows how rotation at large scales can create directional preferences in patterns and structures. Perhaps life's chirality is the ultimate expression of this principle. The universe's rotation, expressed through magnetic fields, starlight and interstellar chemistry, imprinting a twist into the molecules that would become life. Some researchers have speculated that if we ever discover life on other planets, we might find the same handedness. If life everywhere uses left-handed amino acids and right-handed sugars, it would suggest a universal cosmic process, not random chance. Alternatively, we might find the opposite handedness. That would suggest that while the process is universal, the direction depends on local factors. The specific orientation of magnetic fields in each star-forming region, for example. Either discovery would be profound. It would tell us that life's molecular structure is not arbitrary, but shaped by the cosmos itself. Take a slow breath. The proteins folding in your cells, the DNA replicating in your nucleus, all carry a twist, a handedness that may have originated in the polarized light of ancient stars. You're built from stardust that remembers which way it was spinning billions of years ago. And as we trace this thread of rotation through cosmic history, we arrive at a sobering question. If everything spins, if motion is the heartbeat of the universe, what happens when that heartbeat slows? When galaxies stop forming, stars burn out, and the cosmos itself begins to forget how to turn? That's the twilight we explore next. The long, slow unwinding of everything. Part 9. The slow unwinding. When the universe forgets how to spin. Everything that rotates is slowing down. The Earth's days grow longer. Galaxies drift apart, their rotation rates decreasing as the universe expands. Stars burn out one by one, their nuclear fires extinguished. Even black holes, those ultimate engines of spin, eventually evaporate. The universe is not winding up, it's winding down. And billions of years from now, when the last rotation finally stills, what remains will be silence, darkness, the faint memory of motion written into spacetime's geometry, but nothing left to move. Tonight we drift toward that distant horizon, to ask what happens when the universe forgets how to spin. Let's start close to home. Earth's rotation is slowing, gradually but inexorably, due to tidal friction from the moon. Every day is getting longer by about 1.7 milliseconds per century. That sounds trivial, but over geological timescales it adds up dramatically. 600 million years ago, a day lasted only about 21.9 hours. We know this from studying growth rings in ancient corals, which recorded daily tides in their structure. Going further back to Earth's formation 4.5 billion years ago, a day lasted only 6 hours. The young Earth spun much faster, completing 4 rotations in the time we now take for one. Laser reflectors placed on the moon by Apollo astronauts allow scientists to measure the moon's orbital distance with millimeter precision. Each year, the moon drifts about 1.5 inches farther from Earth. As the moon recedes, Earth's rotation slows, transferring angular momentum outward. This process will continue for billions of years. Eventually, if both Earth and Moon survive long enough, Earth's rotation will lock with the Moon's orbit. The planet will always show the same face to the Moon, just as the Moon already shows the same face to us. When that happens, a day will equal a lunar month, about 47 current days. The Moon will hang motionless in the sky, visible from only one hemisphere. The other hemisphere will never see it. Tides will cease, or become very weak, driven only by the Sun's gravity. Earth's rotation, that ancient rhythm that has defined life for billions of years will effectively end. But Earth is just one world. Across the solar system, rotation is winding down everywhere. Mercury is already tidally locked in a 3-2 resonance with the Sun, rotating 3 times for every 2 orbits. Venus rotates so slowly that its day, 243 Earth days, is longer than its year, 225 Earth days, and it spins backward, possibly due to a massive collision early in its history. Mars, with its 2 tiny moons, has no significant tidal braking, so its rotation changes only slowly due to internal redistribution of mass and seasonal effects. The outer planets, the gas and ice giants, rotate rapidly. Jupiter's day is less than 10 hours, but even they will slow, over timescales so long they're hard to comprehend, as their moons and the solar wind gradually sap their angular momentum. Beyond our solar system, in the broader universe, rotation is decreasing on much larger scales. Using the Hubble Space Telescope and ESA's Very Large Telescope, astronomers have measured the rotation of distant galaxies billions of light years away. When compared to nearby galaxies, those ancient systems spun faster. They had tighter spiral arms, denser cores, more vigorous star formation. As the universe expands and galaxies age, their rotation rates decline. Gravitational interactions with neighbours, collisions and mergers, and the slow diffusion of dark matter halos all contribute to this slowing. A 2020 study from the Leibniz Institute for Astrophysics Potsdam found that spiral galaxies lose angular momentum over cosmic time, gradually transforming into slower, more elliptical shapes. The Milky Way and Andromeda are currently approaching each other at about 250,000 miles per hour. In roughly 4 billion years they'll collide. The merger will be spectacular, triggering waves of star formation as gas clouds clash. But the end result will be a single, massive elliptical galaxy rotating more slowly than either progenitor. The beautiful spiral arms, shaped by rotation, will be disrupted and scattered. What emerges will be rounder, calmer, older. ESA's Gaia mission has mapped the Milky Way in unprecedented detail, showing that our galaxy is already changing. The outer arms are stretching, and interactions with satellite galaxies, like the Large and Small Magellanic Clouds, are redistributing angular momentum. Eventually, all galaxies in gravitationally bound groups and clusters will merge, forming giant elliptical galaxies with little rotation. This process is already well underway in dense galaxy clusters. Stars, too, are slowing. The Sun, which rotated once every few hours when it was young, now takes 27 days to complete a rotation at its equator. Stellar winds carry away angular momentum, gradually breaking the star's spin. Old stars rotate very slowly, sometimes taking months for a single rotation. As they age and expand into red giants, their rotation slows even further, the same angular momentum spread over a vastly larger surface. But some stars speed up dramatically in death. When a massive star collapses into a neutron star, it spins faster, conserving angular momentum as its radius shrinks. Newly formed neutron stars can rotate hundreds of times per second, their surfaces moving at a significant fraction of the speed of light. These pulses gradually slow as they emit radiation and magnetic energy. NASA's NICER instrument has tracked this spin down with extraordinary precision. Even the fastest pulsars are losing rotational energy, microseconds at a time, slowing over millions of years until they become too faint to detect. Black holes represent the ultimate fate of rotation. When a massive star collapses completely, beyond even neutron star density, it forms a black hole. If the star was rotating, the black hole inherits that rotation, becoming a Kerr black hole spinning with immense energy. Near a rapidly rotating black hole, space-time itself is dragged around faster than light, creating the ergosphere where nothing can remain stationary. But even black holes don't spin forever. In 1974, Stephen Hawking predicted that black holes emit radiation due to quantum effects near the event horizon. This Hawking radiation causes black holes to lose mass and energy over incredibly long timescales. A black hole the mass of the Sun would take about 10^67 years to evaporate completely, far longer than the current age of the universe. But supermassive black holes, millions or billions of solar masses, would take 10 and 100 years or more. As a black hole evaporates, it loses angular momentum along with mass. The rotation gradually transfers to the emitted radiation, a slow leak of spin into the surrounding universe. Eventually, after incomprehensible stretches of time, even the largest, fastest spinning black holes will fade to nothing, their rotation dispersed into the void. So where does all this angular momentum go? It doesn't disappear. It can't. Angular momentum is conserved, but it spreads thinner and thinner, distributed across an ever-expanding universe. As NASA's theoretical physics teams explain, in an isolated system, angular momentum is conserved. The universe as a whole may be such a system. So rotation never truly vanishes. It just becomes imperceptible, spread across vast distances with no concentrated motion to observe. In the far future, trillions of years from now, the universe will enter what physicists call the degenerate era. Stars will have exhausted their fuel. Only faint brown dwarfs, white dwarfs, and neutron stars will remain, slowly cooling in the darkness. Galaxies will have merged into massive, diffuse structures, their stars drifting apart as gravitational interactions fling some into intergalactic space. Rotation will still exist mathematically, but with stars so spread out, so far apart, there will be no visible motion, no spirals, no structure, just isolated embers cooling in an ever-expanding void. After 1040 years, protons themselves may decay if certain physics theories are correct. Matter as we know it would dissolve into radiation. Even the last remnants of rotational structure, the positions and motions of particles would fade. Eventually, only black holes will remain, slowly evaporating through Hawking radiation. The last supermassive black holes won't evaporate completely until about 10 or 100 years after the Big Bang. When they finally disappear, the universe will contain only a thin soup of radiation and elementary particles, spread across incomprehensible distances. The temperature will approach absolute zero. There will be no gradients, no flows, no reason for anything to move. This is the heat death of the universe, the state of maximum entropy where all usable energy has been exhausted. Rotation will still exist in principle, the universe's total angular momentum unchanged, but there will be nothing to rotate, no structure to spin, no observers to measure it. Cosmologists, including Lawrence Krauss and Brian Greene, describe this as the ultimate cosmic silence. Not an ending exactly, but a fading. A universe so still, so cold, so diffuse that nothing can happen anymore. Some physicists speculate about even stranger fates. If the cosmological constant, the force driving the universe's accelerating expansion, continues forever, we might end in a big rip, where expansion becomes so violent it tears apart galaxies, stars, planets, atoms, and finally space-time itself. In that scenario, rotation would become meaningless, as space expands faster than particles can orbit each other. Every bound system would be ripped apart. Alternatively, if dark energy decays or reverses, the universe might eventually stop expanding and begin to contract, ending in a big crunch. As space compressed, galaxies, stars, and eventually atoms would be crushed together. rotation rates would increase dramatically as conservation of angular momentum forced everything to spin faster. But most evidence suggests the universe will expand forever, cooling and dimming until only the faintest whispers of motion remain. The James Webb Space Telescope, peering back to within 300 million years of the Big Bang, shows us galaxies already spinning, already structured. Motion was there from the beginning, and motion will persist in some form until the very end. But the end is unimaginably distant. For now, the universe is still young, still vibrant, still spinning. Stars are still forming, galaxies are still colliding and merging, creating new bursts of rotation. Planets are still being born in spinning accretion disks. Life is still evolving on at least one world, and possibly countless others. The great unwinding has barely begun. Take a long breath. Right now, Earth still spins, the Sun still orbits the galaxy. The Milky Way still drifts through space. Every motion you know, every rhythm that defines your existence is a flicker of the universe's rotational memory. Billions of years from now, when the last stars fade and the last black holes evaporate, that memory will still be encoded in the geometry of space-time, in the faint statistical distribution of particles across infinite space. Rotation won't be destroyed. It will be forgotten, dispersed beyond recognition, but mathematically present, a ghost of the motion that once filled the cosmos with light and life. And perhaps, just perhaps, that's not an ending but a transformation. Because even when the universe forgets how to turn, the patterns of motion will remain, written into the fabric of reality itself. Which brings us to our final question, the deepest mystery of all. If rotation has shaped everything from galaxies to molecules, from time itself to the structure of life, what are we? The observers of this motion, or part of it? That's where we conclude, with the realization that we are not witnesses to the universe's spin. We are the spin itself, made conscious. Part 10. We are the universe. Remembering its motion. Every atom in your body is spinning. Right now, electrons orbit nuclei at incomprehensible speeds. The nuclei themselves rotate, protons and neutrons bound together by forces that depend on quantum spin. Even deeper, the quarks inside those protons and neutrons carry their own intrinsic angular momentum. You are, quite literally, a collection of tiny rotations, billions upon billions of them, all coordinated into the structure you call yourself. But the spin doesn't stop at the atomic level. It extends outward. You stand on a planet rotating once every 24 hours. That planet orbits a star at 67,000 miles per hour. The star orbits a galaxy at 490,000 miles per hour. And the galaxy moves through the universe at over 1,000,000 miles per hour, carried by forces and flows that began 13.8 billion years ago. You're not separate from this motion. You're made of it, shaped by it. Your very existence depends on the angular momentum that has cascaded through every scale of reality. From the quantum foam of the Big Bang to the spiral of DNA in your cells. Tonight, in this final chapter, we ask the deepest question of all. Are we merely observers of the universe's spin, or are we the way the universe remembers that it's still turning? Let's start with the most fundamental level. Quantum spin. Every particle, electrons, protons, neutrons, photons, all carry an intrinsic property called spin. It's not literal spinning like a top, but a form of angular momentum built into the particle's existence, as fundamental as its mass or charge. Quantum spin comes in discrete units. Spin 1, 2 for electrons and quarks, spin 1 for photons, and so on. These values determine how particles interact, how they bond, and ultimately how matter organizes itself. Without electron spin, chemistry wouldn't exist. the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state, depends on spin. This is why atoms have electron shells, why elements have distinct properties, why molecules form. The chemical bonds that build your proteins, your DNA, your cell membranes, all depend on the precise spin states of electrons. Your existence is an expression of quantum angular momentum, organized into increasingly complex patterns. As physicist Richard Feynman observed, spin is one of the most profound properties of nature. It is not that the particle is literally spinning, it simply has spin as it has mass. So in a very real sense, you are built from spin, not metaphorically, but physically. Every molecule in your body is held together by electromagnetic forces that depend on electron spin states, but consciousness, the subjective experience of being you, emerges from something even more dynamic: neural activity. Your brain contains about 86 billion neurons, each capable of firing electrical signals at rates up to hundreds of times per second. These signals are generated by the flow of ions, charge particles, across cell membranes. The movement of these charges creates magnetic fields, weak but measurable. Every thought you have, every memory you recall, every emotion you feel is associated with specific patterns of neural firing, waves of electrical and magnetic activity sweeping across your brain. In 2019, researchers using advanced magnetoencephalography, (MEG), mapped the brain's magnetic fields with unprecedented precision. They found that conscious thought correlates with synchronized oscillations across different brain regions, coordinated waves of activity that rotate through the neural network. These aren't literal rotations, but patterns of activation that cycle and repeat, creating a kind of temporal spin. Consciousness itself might be an emergent property of these rotating patterns, a way for complex systems to model and predict their environment. From this perspective, awareness is motion. It's the brain continuously updating its internal model of reality, a process that never stops while you're alive. And what is that internal model? It's a reflection of the external world, the spinning Earth, the orbiting Sun, the rotating galaxy. Your circadian rhythms, your sense of time passing, your perception of change, all attuned to the rotations that surround you. In a very real sense, your consciousness is the universe's rotation made aware of itself. The same angular momentum that began at the Big Bang has organized itself, through billions of years of evolution, into a structure capable of recognizing its own motion. Carl Sagan expressed this beautifully. The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. In the language of physics, that knowing is through motion, energy, and spin. The universe continuously encodes its history in the distribution and motion of matter, and in rare, precious cases that matter becomes complex enough to reflect on its own state. You are one of those reflections. Consider the history of motion written into your body. The iron in your blood was forged in the core of a dying star, a star that was rotating, throwing off layers of material enriched with heavy elements. That iron carried angular momentum, a signature of rotation that persisted through the star's death and the formation of new star systems. When Earth formed from the spinning protoplanetary disk, that iron, along with countless other elements, was incorporated into the planet. Later, through geology and biology, it became part of you. The iron atoms in your hemoglobin, carrying oxygen through your bloodstream, are the same atoms that once orbited inside a massive star billions of years ago. The calcium in your bones, the carbon in your DNA, the oxygen you breathe, All were created in stars and carried the rotational signature of those stars. You're literally made of recycled stellar material, and that material remembers its spinning origins through its angular momentum. Even the water in your cells may have come from comets, icy bodies that formed in the outer solar system and spiraled inward, delivering water to the young Earth. Those comets were shaped by rotation, their ices preserving volatile compounds and organic molecules from interstellar space. When you drink water, when you hydrate your cells, you're incorporating material that has been spinning through space for billions of years, carrying with it the chemical memory of ancient stars and molecular clouds. On a molecular level, the chirality of your amino acids and sugars, the left and right-handedness that defines biochemistry, may trace back to polarized starlight in those same molecular clouds. The twist in your proteins might literally reflect the spin of magnetic fields around young stars. So when we ask whether you're part of the universe's motion, the answer is undeniable. You're not just part of it, you're a continuation of it, a local concentration of angular momentum that has persisted and evolved for 13.8 billion years. From a certain perspective, the Big Bang never ended. It's still happening. It's happening in the expansion of space, in the formation of new stars, in the rotation of galaxies, and in the thoughts occurring in your mind right now. You are the Big Bang, still unfolding, still exploring, still spinning. ESA's Planck satellite and NASA's WMAP mission mapped the cosmic microwave background and found those tiny fluctuations, the seeds of structure. Those seeds grew into galaxies, stars, and planets through gravitational collapse and conservation of angular momentum. One of those stars was the Sun. One of those planets was Earth. And on that planet, through chemistry and evolution, matter organized itself into life, into consciousness, into you. The unbroken chain of causation connects the first quantum fluctuations in the Planck epoch to the thought you're having at this very moment. It's all one continuous process, one grand rotation that has never stopped. NASA's Goddard Space Flight Center describes angular momentum as the persistence of spin. What began spinning at the Big Bang is still spinning now. The form has changed, the scale is diversified, but the rotation continues. When you move your hand, you're redistributing tiny amounts of angular momentum. When your heart beats, it's pumping blood in coordinated waves, a kind of circulatory rotation. When you think, neurons fire in cascading patterns, waves of activity that cycle through your brain. All of it, from the quantum to the conscious, is motion. And all of it traces back to that first cosmic rotation. Some physicists and philosophers have speculated that consciousness itself might be a fundamental property of the universe, not something that emerges only in complex systems like brains, but something inherent in the organization of matter and energy. This idea, called panpsychism, suggests that even simple systems have a rudimentary form of experience, and complexity amplifies and organizes that experience into what we recognize as consciousness. Whether or not that's true, it's clear that consciousness depends on motion. A perfectly static brain would be unconscious. Activity, change, the continuous rotation of neural states is what creates awareness. In that sense, consciousness is the universe's motion becoming aware of itself, not through mysticism, but through physics. Matter, organized by billions of years of evolution, reaches a configuration complex enough to model its own behavior, and in doing so, becomes conscious. You are the universe looking at itself, remembering its own history, contemplating its own motion. The atoms in your brain were once in stars. The patterns of neural activity that create your thoughts follow laws that have been constant since the Big Bang. The sense of time passing that you experience is tied to Earth's rotation, which is tied to the angular momentum of the solar system. which is tied to the Milky Way's formation, which is tied to the quantum fluctuations in the early universe. It's all connected. One unbroken thread of causation, one continuous rotation that encompasses everything, from the smallest quantum spin to the largest galactic swirl. And you, reading these words, thinking these thoughts, are not outside that rotation. You're inside it. You are it. As astrophysicist Neil deGrasse Tyson reflected, we're not in the universe. We are part of the universe, and the universe is in us. Take a final, slow breath. Feel the stillness around you, but know that it's an illusion. You're spinning at 1,000 miles per hour on a planet orbiting a star at 67,000 miles per hour, in a galaxy moving at 500,000 miles per hour, through a universe that has been spinning since time began. Every atom in your body carries that motion. Every thought in your mind reflects it. You're not witnessing the universe's spin. You're the spin itself, made conscious, made aware, made human. And perhaps that's the deepest answer to why everything spins, not because some force set it in motion, but because motion is the fundamental nature of existence. To be is to move. To exist is to change. To live is to spin. The universe didn't learn to rotate. It was born rotating. And through billions of years of evolution and emergence, that rotation became complex enough to wonder about itself, to ask why it moves, to create stories and poetry and science in an attempt to understand. You are the universe's answer to its own question. The motion that began in the first instant, organized into a form that can contemplate its own beginning. So when you lie down tonight, beneath the invisible turning of the stars, remember this. You are not standing still. You never have been. You're gliding through a cosmic river, gently, constantly, endlessly. Every moment of stillness is just the universe moving too smoothly for you to notice. And in that perfect balance of motion and calm, life finds its quiet rhythm. You're spinning, always have been, always will be, until the atoms that make you scatter and join new rotations, new structures, new expressions of the universe's endless motion. And the silence you hear, the peace you feel, is simply the sound of everything moving together in perfect harmony. Closing. If this quiet journey through the cosmos has brought you even a small moment of peace, even a gentle shift in how you see the spinning world around you, I'm deeply grateful you spent this time here with me. A gentle like or a soft tap on subscribe means more than you can imagine. It's what keeps me creating these cosmic lullabies for wandering minds like yours, these explorations of the beautiful, strange, spinning universe we call home. And if you're kind enough, please tell me in the comments where you are tonight, what time it is where you're listening, and whether you'll ever feel stillness the same way again. I love seeing how far these quiet adventures drift across the world, from one corner of our spinning planet to another. Your words, your presence, even your silence. They're like little stars guiding me forward, and I treasure them deeply. Until next time, may the universe turn softly around you. May you remember that every moment of calm is just the cosmos moving in perfect harmony. And may you carry with you the knowledge that you're not separate from the great cosmic dance, but an essential part of it. You are the universe, spinning, thinking, wondering, and that perhaps is the most beautiful mystery of all. Good night, fellow traveller, keep spinning.